So each term in the sum takes its speed from either the left-hand side of the interval or the right-hand side of the interval. When I was doing my underestimate, I was always picking the left-hand side. So when I looked at 0 to 50, I picked the speed on the left. When I was looking at 50 going to 55 miles per hour, I always picked the speed on the left. And then 55 to 65, I picked the speed on the left. 65 to 75, I picked the speed on the left. So each term takes its speed from the left-hand side, so this is what we would call a left-hand sum. In this case, because those were always the smaller speeds, it gives us an underestimate of the total distance. Now, in the overestimate, when I looked at each one of the intervals in that case, I always took my speed from the right-hand side. So when I went from 0 to 0.5 hours, I had a choice of 0 or 50 miles per hour. I picked the higher one, and that just happened to be on the right-hand side. And the same thing was true when I went from 0.5 to 1, or 1 to 1.5, or 1.5 to 2. I always go ahead and I pick the higher value, and that value was always on the right-hand side of the interval. So since each term takes its speed from the right-hand side of the interval, this is called a right-hand sum. Now let's get this idea of what this all means geometrically. From what we've seen before, we've been undoing the rate because we've been taking miles per hour times hours, and that was giving us miles. So here I've gone ahead and I've graphed the data points that we've had in the previous table. And now what I'm going to do is I'm going to show you what each one of these pieces means geometrically. So for instance, let's take a look at the term where we took 50 miles per hour times a half hour. And let's put that on our graph. So if I draw a rectangle that goes from 0.5 to 1, so it's 0.5 wide, it's also 50 wide because this rectangle touches on the left-hand side, and that point was at 50. So when I say 50 times 0.5, that's like finding the area of this rectangle that's 50 high by 0.5 wide. So in that way, that term corresponds to the area of this rectangle. If I go to the next term, it was 55 times 0.5. Well, I can draw a rectangle that's 55 high and 0.5 wide, and that area corresponds to the value of that term. When I go to the next term, it was 65 times 0.5, so I'm going to draw a rectangle from 1.5 to 2 that is 0.5 wide and 65 high. Notice that this is also touching the data on the left-hand side of that rectangle. The last thing I'm going to do is I'm going to draw a rectangle that is 0 high and 0.5 wide, and that's just this little sliver here. It actually shows a little bit of area, but I wanted to make sure that I showed you that there was actually a rectangle there. It's just kind of a silly rectangle that's only 0 high and 0.5 wide. So if I sum up those areas, that's like adding these four terms together. So the total area that you see in red here is the same as the sum of these four terms, which gave us a total of 85 miles. Let's try the same thing now with the overestimate. So our first term was 50 times 0.5. So over the first half hour, I'm going to draw a rectangle in that's 50 high. So it touches now on the right-hand side. And it's 0.5 wide. So the area of this rectangle corresponds to this term of 50 times 0.5. The second term means that the rectangle needs to be 55 high, and it touches on the right-hand side to the data, and it's also 0.5 wide. So the area of that rectangle corresponds to the term 55 times 0.5. The next rectangle is 65 high and 0.5 wide, So the area of this rectangle corresponds to the third term, or 65 times 0.5. And you guessed it, the last term is 75 high, so it touches on the right-hand side. It's 0.5y, so the area of that rectangle is 75 times 0.5. That corresponds to the last term. If I were to go ahead and add up those rectangles, their areas, I would end up getting 122.5 miles. So what we're noticing is that the area here corresponds to these terms. So let's go ahead and expand on this concept. What you see here is I've gone ahead and shown you the formula f of x equals x squared plus 1. And what I've done is I've shaded in purple here, the area that goes from 0 to 4. And what we're going to now try and do is find what this area is by using rectangles like we've just seen. So let's start and let's find the area from 0 to 4 underneath this curve. But to do this, we're going to start with using two rectangles. Now clearly, if I find the area of these two rectangles, it's not going to be the area of this entire region. But what I'm hoping is as I add more and more rectangles in here, making them narrow and narrower, it's going to get closer and closer to that area. So I've got two rectangles here. One that goes from 0 to 2 and another one that goes from 2 to 4. And they each have some heights. Up here in the blue box, I've actually shown the two terms that correspond to those two rectangles. Notice that these two terms both have a 2 in them. And the reason for that is both of the rectangles were too wide. Now I need to find how high they are. And in this case, both of these rectangles take their height from their left-hand side where they touch the purple curve. So where 0 goes into this function, and when I put 0 into this function, f of 0 is 1, so this rectangle was 1 by 2 wide. So it was 1 high, 2 wide. The second rectangle also takes its height from the left-hand side, and that means I need to put 2 into this function, and when I put 2 into here, 2 squared plus 1 is 5, so this rectangle is 5 high, 2 wide, so the term up here is 5 times 2. So the area of these rectangles, which is going to be an underestimate of the actual area, is 2 plus 10, or 12. Now let's use more rectangles. If I use more rectangles, I'm going to get closer and closer to the actual area under the purple curve from 0 to 4. Notice all of these rectangles touch on the left-hand side. So when I go to this first one, this is like the one that we had before that was 1 high, but now it's 1 wide. So this term is 1 times 1. The next term is 1 wide, but now when I put 1 into the curve, I get 1 squared plus 1. That's 2 high. So this is 2 units by 1 unit, so 2 times 1. If I go to the third rectangle, what you'll notice is that it takes its height at x equals 2. So when I put 2 in here, I get 2 squared plus 1, that's 5. So this rectangle is 5 high, 1 wide. So in my sum up here, I have a term that's 5 times 1. The last rectangle is at 3, its left-hand side is. So when we put 3 in here, we get 3 squared plus 1, or 10. So this rectangle is 10 high, 1 wide, so 10 times 1. So when we take 1 times 1, plus 2 times 1, plus 5 times 1, plus 10 times 1, I get a total of 18 units. And again, this is an underestimate of the area because I'm not getting the area in these little triangles here. Now let's go ahead and add even more rectangles. And now notice that that first rectangle, it's still 1 high, but now it's only 0.5 wide, so the term is 1 times 0.5. The next term comes from taking a half and putting it into the function. So when I do that, a half squared is 1/4, plus 1 gives me 5/4, so it's 5/4 wide, a half, or 5/4 high, and a half wide, so that means 5/4 times 0.5. We can continue to do this for every single one of these rectangles till I get all the way to the very last one. Then I put 3.5 into x squared plus 1, and what I get is that it's 53/4 high, 0.5 wide. So if I add up all of these 8 rectangles here, I'm going to get 1 times 0.5, 5/4 times 0.5, all the way up to 53/4 times 0.5, and that gives me an area of 21.5. Notice that the only difference from the previous example when I had fewer rectangles is now I'm still touching on the left-hand side, but they have a different width here. So I can continue to go ahead and increase the number of rectangles here. In this case, I've got 16 rectangles, so I'm going to have 16 terms up here. And for instance, the first one is still 1 high, but now it's only 0.25 wide, so the first term is 1 times 0.25. The next term here takes its height from 1/4 put into the function. When you put 1/4 into the function, you get 17/16 times 0.25 wide. I do that for all 16 of these rectangles, which is going to give me 16 terms up here. And what I get now is an area of 23.375. And notice that the amount of area that we're missing here is a lot smaller. So we're getting closer and closer to the actual area. So if I increase even more, now it looks like what I have here is 40 rectangles. So I'm going to have 40 terms to this sum. I get an area of about 24.54. So now let's do it, but using overestimates. So when I do an overestimate, now when I look at that first rectangle, I'm going to take the height from the right-hand side. So in each one of these 2 rectangles now, you see that it's touching the curve on the right-hand side. So now when I look at the first rectangle, its height is going to come from taking 2 and putting it into the function, which means 2 squared plus 1, which is 5. So 5 high and 2 wide. So I'm getting too much area here, so this overestimate of that first rectangle is going to give me 10. Now when I go to the second rectangle, it takes its height from the right-hand side, which means I put 4 into the function. 4 squared plus 1 is 17, and it's 2 wide. So my overestimate of the area from 2 to 4 is 17 times 2. So when I add up those 2 areas, that's 5 times 2 plus 17 times 2, I get an area of 44. That's way too much, but we can get better and better estimates by using more and more rectangles. So let's do exactly what we did before. We're going to go ahead and add more rectangles, and as we do that, we're going to see that we get closer and closer to the actual area. So now if I go to 4 rectangles, that means each one of them is 1 wide. The first one takes its height from putting 1 into the function, which is 2. So it's 2 times 1 for the area. The second rectangle takes its height from putting 2 into the function. That's going to give me 5, so 5 times 1. The third rectangle takes its height also from the right-hand side. So when I put 3 into the function, I get 3 squared plus 1, which is 10, times 1 for the width. And then the last rectangle takes its height from the right-hand side, which is at 4. When I put 4 into the function, I get 17. So this last rectangle is 17 high and 1 wide. So the 4 rectangles give me terms of 2 times 1 plus 5 times 1 plus 10 times 1 plus 17 times 1. That's a total of 34 units of area. I can continue to increase the number of rectangles. So now I have 8 rectangles in here. And when I do that, I see my terms become 5/4 times 0.5 plus 2 times 0.5, a whole bunch more terms, and then the very last rectangle is 17 high and 0.5 wide. That gives me a total estimate of my area of 29.5. Again, notice that it's an overestimate because I'm getting too much area. But as I add more rectangles, I'm getting closer and closer to the actual area. The overestimate is not nearly as bad. So now I've gone ahead and I've added even more rectangles here. Now we're up to 16 rectangles, and I get, for the first rectangle, the area is a height of 17/16 and 0.25 wide. The second rectangle is 5/4 high and 0.25 wide. And I can continue to go to each one of those 16 rectangles till I get to the very last one, which is 17 high, 0.25 wide. Add all 16 of those terms up, I get 27.375. Now I've added even more. Now I'm up to what looks to be about 1, 2, 3, 4, 5. This looks about to be 40 rectangles here because there's 10 rectangles from 3 to 4. So if I go from 0 to 4, there's 40 of them. Now I see an area of 26.14, but to get that, I'd have to add up all 40 of those terms. So let's look at a summary of what I've done so far. I worked out for 2, 4, 8, 16, and 40 rectangles what the left-hand sum was. That means each one of my rectangles touched the curve on the left-hand side, and a right-hand sum, which means each one of the rectangles touched on the right-hand side. So when I had 2 rectangles, I had an underestimate of 12, but an overestimate of 44. When I had 4 rectangles, I had a underestimate or a left-hand sum of 18 and an overestimate or a right-hand sum of 34. And what you'll notice is I increased the number of rectangles. I got these 2 estimates, the left and the right-hand sum, to be closer and closer. So when I get all the way out to 40 rectangles, the left-hand sum, which is an over or an underestimate, is 24.54 units of area. The right-hand sum, or the overestimate, is 26.14 units of area. So now they only differ by about 1.5. Compare that to the 12 to 44, we're doing much, much better. And I could continue to go ahead and add more rectangles, and these estimates would zero in on a value that looks to be somewhere around 25.